Nice. Thank you so much, Dwan, and it's so good to see everybody and such a wonderful set of presentations for the morning as well. Today, I'm going to start by giving kind of our view. By the way, my name is Brad Rothenberg, CEO, founder of nTopology, now called nTop. We shortened our name or lightweighted the name. I'm going to give our view on how we think about computational design, computational modeling. And then I'm going to be joined by one of our local customers from Siemens Energy, Markus Lempke, as well, to kind of talk through some applications that he's been working on. And then I'm going to finish up with some peeks into nTop 5 that's coming soon as well. So, first off, the way that we think about computational design, we think computational design is best applied to the really hard physics-driven problems where iteration is really key through the process. And this is a AM conference, but I thought it would be interesting to start with a non-AM example. From one of our customers at Tesla, I think the gigacasting kind of exemplifies these problems, and they've been working on this for much longer than we've existed as a company even. But taking 70 individual metal stampings from the rear underbody of a car and redesigning that into 2 gigantic metal gigacast components requires consistent iteration. It's a very physics-driven problem. The geometries, back in my days in architecture school, we said form follows function. It's very much the form is driven by the simulation, by the physics. But moving into AM, AM introduces even additional complexity into the process. You're forming the shape and the material. You're forming the material while you're generating the shape. You can print shapes that you couldn't design or you couldn't manufacture with other processes. And when you look at kind of the current status quo engineering tools and the way that they were not built for computational design back in the long before I was born, and probably almost many people in here were born. They weren't built for computational design, and while great, I started nTop because I was obsessed with CAD, really into 3D modeling software. The manual processes, the manual modeling of low-level design features up front, it's very limiting to the process. You need to manually draw. This is a screen grab from some of our customers at Lockheed Aero modeling the bulkhead ribs, and they literally manually click on each rib and design fillets for each of those ribs. Second, it's very tricky to kind of set up relationships between geometry in a parametric CAD system. Like, for example, this is a manifold for a rocket intake, and what you'd want to do is have the manifold diameter changing over the course of the curve while it joins together based on kind of some target pressure in and target pressure out. Where those 2 pipes join together, that parametrization might break because of the way it needs to be defined with a traditional model. And then lastly, capturing the physics that's driving these parts and products is very difficult. It's difficult to capture, and then even if you can capture it, using those physics to drive the relationships between geometry is also, it's very difficult as well. And so when we think about computational design, I think of it as a new process, right? And so looking at the kind of oversimplified engineering process, right? Like, you start with the design, you mesh it, you simulate. You start with the design, redesign it, mesh it, simulate, et cetera, et cetera, et cetera. And, more iterations should ultimately lead to more performance. Each iteration, you're learning something new, you're learning something new, you're learning something new. And so within a computational design process, the way that we think about it is really three steps. One, you build a computational model. So you kind of encode the logic of the design with inputs and outputs. Once you have that model built, you can then run it to come up with what the optimal design is based on some target, fitness criteria. And lastly, you need to integrate that design into a larger system, right? So you need to go back into your CAD system for the assembly. You need to go into CAE for further downstream validation. Maybe you need to do fatigue analysis, creep analysis, et cetera. You also need to get into CAM tools for manufacturing as well. And so, the current processes ultimately leads to this business problem where, you're only getting a certain number of iterations in per time that you have, right? It's manual. With the computational design process, maybe it takes a little bit longer up front to define that model if you could also draw it in a CAD system. But the power of this process is that once that model is defined, you can rapid fire iterate through the design kind of automatically or in collaboration with the computer to kind of get to those better results. And so you can get an order of magnitude more design iterations in the same amount of time. And so, if the limiting factor in a traditional process is how quickly you could model something, the limiting factor in computational design is compute. How quickly can we compute these results? How quickly can we solve them? And so at nTop, we kind of think about building tools purpose-built for this computational design process. First off, we have a software, nTop. It's the desktop software based on this really powerful modeling technology, which I'll show some previews of at the end here, using signed distance fields to capture the geometry. So it's fast, built for modern computers on GPUs, and it's very robust. Second, we have a product, nTop Automate. You could think of nTop Automate as like nTop robots that are cloud deployable to process and run these models for you to create the results. And then lastly, we have a product called nTop Core. nTop Core is for our partners to kind of integrate the implicit model into their design ecosystem. And we've had some exciting announcements last year and some more exciting announcements to come as well, in that it's a relatively easy SDK. You read in the nTop generated implicit. You can query the implicit for its distance or for its gradient, or you can extract a mesh, or you could extract contours from that. And so definitely this is open to all of the kind of new tools in the room as well. Excited for you guys to integrate and build on top of some of the work that we've done, because we put a lot of time, a lot of effort into producing these tools, really purpose-built for computational design. And so, as of today, we're in about a little over 400 customers, kind of across the space, across aerospace, medical, automotive, industrial, consumer, and manufacturing. And so I'm really proud and excited to be joined, as we're in Berlin. My first time in Berlin was actually to meet with Markus and the Siemens Energy team several years ago, and it's just been exciting and impressive. I mean, little quick story, which is when I first met Markus and the team, they were like, okay, we're deploying 3D printing to help with the conversion of our large gas turbine engines to hydrogen power. I learned last night that the hydrogen power is basically for better energy storage, so you can collect the energy when it's cheap, store it in hydrogen, which is obviously renewable, and then you can burn it when the energy is expensive. And it was really exciting to hear that they now have large gas turbines running fully on hydrogen with a lot of 3D printed components enabled by 3D printing, really. And these large gas turbine engines, I think, are some of the most advanced products I've ever seen in my life. Like, I think they define simulation-driven design. Think like the jet engine, like a 777 engine is probably like, I don't know, the size of this screen. Well, think about that, but the size of like a tram. That's how big these engines are. It's unbelievable. And so with that, I'll have Markus kind of explain some of the work that they're doing. Thank you.
Yeah, thanks a lot for the introduction. Actually, before I dive into the applications, I have a public service announcement to make, because we often realize that people don't understand yet fully that Siemens and Siemens Energy are now two completely separate companies. We both deal with AM. However, Siemens is really mostly focusing on the software side of things, whereas our goal, coming from the gas turbine business, like we just heard, is really around serial production of LPBF parts in particular. And not only do we do that for ourselves, but through our service provider and our locations, we also service external customers in the aviation and space, automotive, and tooling industry, which gives us quite a unique situation where we really see an array of applications, but we can leverage also our internal knowledge and offer it to external customers. And just a quick view, we'll have a global setup, and just to stress the serial production part, this is by now not the most accurate slide anymore, but you can see we really have large printer fleets. We have 28 LPB, more than 28 printers in Worcester and 19 in Finspång. Those are our serial production facilities, but we also have smaller locations, and in particular the one in Berlin, where we do a lot of our R&D work. Okay, so much about AM at Siemens Energy, and here we are again, another heat exchanger. For me personally also, that was the gateway drug into implicit modeling, because this definition that Brad talked about with the sign distance field, that's really ideally suited for the triply periodic minimal surface structure. What you see on the left-hand side here is one of our latest designs, and I mean, you can always argue how large does the STL file really have to be, but for me to be content with the quality, and that I'm sure that when I put it on the printer, I will not see facets when it comes out, I came up with, okay, roughly needs to be around 5 gigabyte in the print file. Even if I run CFD on it, I still need to export the fluid domains, and both of them come also out at least 1.5 gigabyte. For me, that's just too much to handle. I have, my hard drive is full, and sending that to the printer is a real nightmare when you think about serial production. Whereas with the .implicit format of nTop, where you basically then have it represented as the sign distance field, the print file is 6 megabyte. I can send it to an EOS printer, it gets sliced and vectorized. And what you see here on the right-hand side, that's actually a larger prototype model that we built. It filled up nearly complete M290. And there was just no way in hell that we could do that with an STL, or at least we didn't want to. I know there's people out there that do 30, 40 gigabyte STLs, but I don't think that's a good approach. What is also very special about the implicit modeling to me as a designer, it gives a lot of freedom to adjust the geometry. I mean, we've also seen just in the demo, right, how with the point cloud you can basically affect the structure, and the same is true here, just we're not using points and using fields, and basically it's again the bias that we just heard about. In nTop it's called the wall offset, right, like how far do I put the center wall to the left and the right, and by just having this field that gives me different values, I can then really blend geometry into each other, right? I don't need even a bevel anymore. I can just go ahead and have the two walls collapse, and the channel vanishes just by itself. That's basically what you see in those 45 and 35 degree regions here. At the same time, you also see this shade going from green to orange. That's also just changing the bias, and that is important in a heat exchanger, because with temperature, the density changes, and therefore the volume flow changes, and all this has an impact on your heat transfer, but also especially on the pressure loss. And if you want to have a maximum heat transfer for minimal pressure loss, this is one of the levers that you can work with. Compared to a lot of the other examples that we saw, this is not fancy at all. That's really a very simple heat exchanger we're looking at right now. Usually they are conventionally manufactured. However, we do have customers, internal customers, that very often have a very unique situation, like they need a very unique shape, or it really needs to be fine-tuned to certain operating conditions that they need. And so additive still can be a very viable option there for them. So we were approached, and in order to find the optimal design, I looked at, okay, how can I set up a very lightweight parameter optimization, right? I first said, okay, I want to build it upright, so I'm going to take care that the walls are at 45, 135 degrees. I wanted to have some stagger and some basic dimensions that I can change. I ended up with 4 parameters, and what you can see in the GIF here, that with just these 4 parameters, you can actually create quite a lot of different shapes already. And in the beginning, I also tried to do something like this in a traditional BREP software, and I can tell you that didn't work out so well. It's implicit. The implicit modeling approach here is really much more robust, which I think is an absolute must when we're talking about optimization. I then went the very traditional route. You can go from the science distance field to an SCL. I imported that in just standard CFD solver to get the temperature and pressure loss information, and I then used an optimizer to close the loop and vary the parameters to get a design that I wanted. In this case, I went for a Pareto study just to figure out where I really want to go. I have 2 conflicting targets, pressure loss and heat transfer. As you can see on the bottom left, the horizontal and the vertical lines, these denote my limits that I have to stay under, and there's only a very small portion of the Pareto front that actually even is in the area where I need to go. But what I really want to highlight here is that I came up with quite a robust tool chain, however, optimization chain. However, given that it's a very simple example where I took a symmetric submodel, it still already takes quite long. Yes, I'm computing that on my local workstation, but still, if you look at the time that is spent for just converting the implicit model into a surface mesh and then volume meshing it in the CFD solver and then having the CFD solve, you know, we end up with an average time for the loop that is 1 hour. I calculated 200 designs. You can do the math how long that took. However, it is quite robust. I mean, for me, doing optimizations, only having 23 out of 200 designs fail, that's already a good day. I also have to say this is a real example, so I didn't take out anything. 8 of those designs, that was just because the license server was down. So that's not the fault of any software, that just happens, right? But all the rest of the failures, they actually revolved around surface meshing and volume meshing, which gives me the conclusion, okay, this meshing, that's something that is something that takes a lot of time and is error prone. So is there maybe something we can do about it? And therefore, I'm really happy that we could also partner with Cloudfluid, that are currently partnering also with nTop to look at a different approach. I put the meshless in quotes at the specific request of Max, because it's not really meshless, right? It's basically, you can call it a voxel grid, but that's a completely different thing than a finite volume mesh in the end, right? So on the top, you have, again, the traditional approach, and at the bottom, you have this tighter integration between nTop and Cloudfluid that eliminates certain steps completely, and also the solving of the CFD is actually very performant working on GPUs. So very important is that nTop, that Cloudfluid, that's also a lattice-Boltzmann solver. You basically end up with LES compared to the RANs. So you get in-stationary results. And this can read in directly the .implicit file, right? Which already means that I can just cut out the surface meshing step, and then it actually uses nTop core and the functionalities there to do the voxelization, and boom, that takes less than a minute compared to the 15 minutes I would spend on this specific case for the volume meshing. The solving is also working really fast. I have to admit there's still a lot of things to work out. This is in an exploratory state, but these examples have me quite happy already, and I want to really explore that more. I really think, and we referred a lot about meshless processes, I really think that can also be a huge time saver, which would be very important for everything with the optimization. And now, finally, back from the heat exchangers, more way to our core business. I brought this vane for you that we've been, well, this one we're mainly using, I would say, as a technology example that we can freely show everywhere and share with everyone. Obviously, we have much bigger ones as well. So this is supposed to be a vane 1 that you would see after the combustion system in a gas turbine. And obviously, due to its shape, we have to use quite a lot of support structures to support it, to make sure that it doesn't warp in a way that we don't want, and just for the heat to get conducted to the build plate. On the left-hand side, you basically see where we're coming from. That would be our regular approach with just solid supports, and this can be this has a very huge cost impact, right? We print them. We have to design them, then we need to print them, and then we need to remove them. So 3 times it's just pure waste, and whatever we can take away of those, it's going to be really good for us. So the idea was to use thermal-driven lattice optimization that we use Ansys software for to come up with a way that we can actually have a TPMS structure rather than the solid supports, but still be able to hold the vane in place, fully supported, and eliminate hotspots that would otherwise occur in the build process, right? So this is the example I'm showing. In the first step, we only actually started with a gradient in one direction, varying the thickness. But already this gave us a really, really strong benefit and just showed that what we had done in the simulation, we could put it on the printer and get a real part out. And the benefits were already huge, with 50% less support material and 20% less print time. And for us in serial production, that means a lot of money that we're saving. We're now taking it one step further. That's the overall flow chart. And we're not only taking the solid supports and making them lattices. Now we're basically, together with, Ansys is developing it with our input on our example for us. We are looking at a combined topology optimization with the lattice. So basically, there's now, you can either have void lattice or solid material in the optimization, and all this happens in a lattice meta model. So in the Ansys software, the process simulation, that's completely done. And the optimization is completely done without any defined geometry, but it's done with a model. And then in the end, we end up with the topology shape, the new shape, and the density field of how dense the lattice needs to be. And this is then again where nTop comes into play with this very elegant description of the TPMS structure. And the ability to do field-driven design. We just take in the topology body and a field, and like this we can then create the final geometry. And this, again, would probably create, if you mesh it, well, we know that it creates a large STL again, but with the implicit interop, we again now have the ability to go directly to the printer from a very small file. And as my final slide, just really the latest and greatest that we just produced on Saturday. This is what it then looks like if you do the optimization together with the topology optimization also. And because that's work in progress, we don't have numbers yet, but as I told you, that was 50% already material reduction, and we're looking at 30 to 40% more now with this kind of support structure where we also go to very, very thin walls. Yeah. So I really just can say all those people that talked about, well, we need a paradigm shift in design software. I'm a designer and I agree with you 100%. There's good things out there. We started to leverage implicit modeling and field-driven design in nTop, and that's become a really huge and important part of our computational design toolbox. So we would also be very happy about what Brad suggested, you know. Have integrations, collaborate wherever you can, because I think that will create then even more value.
Thank you, Markus. I mean, I think what's most impressive is the control over the fields and the field-driven design to kind of get that precision and accuracy in the design, the precision and control over the design, which I'm going to come back to and touch on at the end of this. But I wanted to start just to review. So in 2023, you know, we shipped over 130 new features. We release software roughly every 2 weeks, not quite 26. I think there was a couple misses on releases, potentially, or maybe holidays, something like that. But 3 new features from 2023 that are getting some traction in the market. One, our field optimization framework. So this is a multi-objective optimization framework built kind of as an extension of our topology optimization that allows you to use kind of the metamaterial properties of lattices in the optimization framework. And there's actually 2 PhD students here, Peter and Rebecca, who just published their PhD. They did an internship with nTop, kind of contributing to this framework. The term is called dehomogenization in the industry. So I urge you to find them, Ole students. They're in the crowd here, and it's really, really impressive work. Second, we released nTop Automate, which I had mentioned earlier, and nTop Core to enable the implicit interop. And so I'll start with a couple of enhancements to our software. One, obviously, when we're dealing with precise geometry and control over the geometry, you really need to understand what it is that you're building. And so we're introducing a number of new fields to the software, a better viewability of the fields, things like thickness, draft angle, etc. On the analysis side, we've been working with some of these, we put in quotes, mesh-free. It's not mesh-free. Extended finite element method still uses a mesh. It just happened to use a mesh that's maybe more suitable for GPUs and parallel compute, which is a structured grid. This is developed kind of in collaboration with Kurt Mate from CU Boulder as well. This is just kind of showing, by cutting the cells through the mesh, the analysis could handle kind of much more complex structures like these thin shell isogrids and stuff like that. Second, too, is more implicit interoperability. And so in 2023, we announced integrations with EOS and Autodesk. Autodesk will go live in about a month or so, which will come out in Fusion to be able to read in nTop implicits into Fusion and do downstream operations from those implicit models. 2024, we're working with about 15, a few more than that now, nTop Core partners. And the goal is really to build out the implicit ecosystem so that more tools could read in implicits, slice them, do analysis on them, go back into a CAD system, make drawings, do CNC toolpaths, etc. Additionally, CFD is a major topic to our customers as well. You could see in the heat exchanger examples or fluid flow examples. So I'm really excited about integration with SimScale that will come out. David is in the crowd. And then GPU accelerated fluid solvers. Max from Cloud Fluids in the back there, definitely say what's up to him. Again, not mesh-free, but using a voxel-type grid approximation of the geometry, which again is more suitable for GPUs, right, with the regular grid. So this is very fast We've seen some example problems that would have run in weeks in a normal, traditional, finite volume-based CFD system running Cloud Fluid in about a day or a little bit less than that. And in some cases, we can bring it down to an hour. And then lastly, coming to nTop Core is also parametric interoperability. And so this was a demo we made in the early days of nTop Core, where some of the geometric parameters that drive the model can also be exposed for further gradient-based optimization processes. And that exists in nTop today with the field optimization. It's a term that I think Blake Corder may have coined, differentiable engineering, or maybe that's a term. I'm not entirely sure if he took the term, but I think it's a really good term where the idea is to kind of trace back to optimize over key design parameters, right? Like if you have some design parameters, you have some fitness results, and you have a shape that's output, you can basically, using the derivatives and the chain rule, kind of tracing back the derivatives all the way from, the actual, from the fitness to the shape to the parameters. The nTop implicit via nTop Core gives you the derivatives of the shape. It gives you the parameters. Through our nTop Core partners, they can then evaluate the fitness of that shape itself so that you can do further optimization. And so this is kind of an example where field optimization is doing this. There happens to be one parameter here that's spatially varying across. This is an overly simplified cantilever beam example, but it's one parameter varying the shell thickness of the beam that's optimized. And so by doing this, we're basically decoupling the geometry from the physics, so that the idea is any implicit model that's parametric could be tied to any physics optimization to kind of create these more optimal workflows. And then lastly, we're releasing nTop 5. So nTop 5 is coming out in a few months, and the features around nTop 5, more to come soon on this, but really the three areas we're highlighting are we're doubling down on the precision and the speed and introducing more of this interoperability. And so just a little demo here. This was a model that I had made on an airplane on the way coming here. Looks like it's a little bit pixelated from the video, but this is a simple parametric implicit, and as you can see, you can change the parameters. They update in real time in the model. Okay, now it's actually a better view, so it cleaned up. So you can edit these parameters. This is evaluating the model on the GPU in real time. And any of these design parameters, as you change them, right, they theoretically could be tied to these kind of black box optimization that I was mentioning. But one of the issues with nTop is, as you zoom in, you kind of see the voxelization or the rendering of the model. So you would need to press Control H in nTop to get the high resolution view. We put a lot of time into a new modeling engine and a new rendering technology that basically, if you switch it on, it renders it in high precision in real time as you're navigating through the model. And so that enables you to kind of control features that are, in millimeters or, in very, very small over the whole course of an airplane, like if this was some kind of cooling system or antenna in the nose of the plane. And so, when you open that as a model, we have these packaged custom blocks, so you can kind of see inside of the model. You can start to see all of those features resolved at the precision of the actual geometry. Because again, that's the power of the nTop, the implicit, is that you're resolving actually smooth surfaces, sharp features, sharp corners. And so again, if you zoom in here, there's a part of the plane is cut out in the nose just to kind of highlight how precise and small the features are. Oops, it was the wrong direction. So you can, if you zoom in and turn on that antenna view. So this happens to be a conformally mapped structure to the nose. And again, you can see, if you zoom in, it re-resolves, re-updates the rendering, again with like perfect sharp features, precise. And so again, with nTop 5, it's really about, for us, doubling down on the precision, doubling down on the control of that geometry, and giving the tool set so you can view and see these while you're working, while you're building that computational model. And so with that said, super excited about showing this to people, getting more customers using the software, and it's awesome to see everybody here. So thank you.